So hopefully we've already memorized this formula for the angle between two vectors is given by the dot product of those vectors divided by their norms. Or another way you can think about this, since the angle between vectors doesn't depend on the length of those vectors, another way that I just like to think about this is it's like, what if you just normalized those vectors and then took the dot product? That would be the same thing. It's like the dot product between those normalized vectors. Because again, this angle between the vectors doesn't depend on the length of the vectors. And so if you normalize them, that's how you come up with this little formula. But, all right, we're going to try to move quickly here. So if we know that u dot v is equal to 0, so I don't know what the vector u is, I don't know what the vector v is, but if I know that u dotted with v is 0, what does that say about the angle between the vectors? So that means theta has to be what?
Integer multiple of pi over 2.
Sorry, you said a multiple of pi over 2?
Yeah, integer.
Yeah, an integer multiple of pi over 2. No, I don't think so. You're close though. So the formula that we have memorized, the formula from Thursday, I think was cosine of theta is equal to u dot v over u norm v norm, like this. And so what I'm saying is u dot v is 0, which means that cosine of theta is 0, which means that theta has to be pi over 2 plus any integer multiple of 2 pi. Or just pi, right? Can you just do an integer multiple of pi? Does that work? Yeah. Yeah, okay. So anyways, what I was going to actually say originally is just that theta is equal to 90 degrees, which means that, I mean, it's the same thing, but if the dot product of two vectors is 0, then we can think of those vectors as being like perpendicular, right? And anytime you have two vectors u and v that are perpendicular and you take the dot product, that dot product always has to be 0. Right? So that's just a consequence of this formula that we have.
That is with the odd integer multiples, not the even ones. Excluded the even ones. Except pi and its multiples.
So you're talking about this again?
Yeah.
No, it shouldn't. It should be every integer multiple of pi works, because pi over 2 works, and then 3 pi over 2 works, and then 5 pi over 2 works, and then.
The odd.
Oh, so you're saying okay? You're saying this pen, I hate it. I mean, I love it. That's why I use it, but okay. Here we go. So, okay, what Abdullah is saying is that if you had some number here, then this is odd. Yeah. Okay. Anyways, so if the dot product is 0, then we say that, those two vectors would be like perpendicular if those vectors were on the plane. And here's a new definition. We're going to use this word moving forward. The word is orthogonal. So if two vectors are orthogonal, then their dot product is 0. So in a way, orthogonal kind of means the same as perpendicular. It means the angle between those vectors is pi over 2. Or the angle between those vectors is 90 degrees. Now, I already typed this out, but if the two vectors are in the plane, so we're talking about two-dimensional vectors, then when the dot product is 0, we call them perpendicular. Orthogonal is a word that we use to generalize the concept of perpendicular to higher dimensions. So these vectors are orthogonal, because if I take the dot product u dot v, that would be 1 times negative 4 plus 2 times 2. So that would be negative 4 plus 4 equals 0, right? And since the dot product is 0, we would say that those are orthogonal. Since they're two-dimensional, we would say that they are perpendicular, right? So this would be my vector u. V is negative 4 in the x direction and positive 2 in the y direction, so this would be like v. And so u and v would be perpendicular, because they live in the plane, like that. Whenever we're talking about higher dimensions like this, a and b are now 5-dimensional vectors, we can say that these vectors are orthogonal because a dot b would be 1 times 6 plus 2 times 0 plus 0 times 7 plus 3 times 0 plus 2 times 3, negative 3. So that's 6 plus negative 6 is 0. The dot product between a and b is 0, so that means they're orthogonal. But again, since they're not two-dimensional vectors, it would sort of feel strange to call them perpendicular, you know? And so we're going to use the word orthogonal to be a general kind of perpendicular that applies to any vector of any dimensions. Okay. Just a quick example problem. It says find the angle between these two vectors. So we know we have cosine of theta is equal to u dot v over norm u times norm v. So cosine of theta is going to be the dot product between u and v. So that would be 2 times 3 plus negative 1 times 0 plus 1 times negative 1 is going to be 5 divided by norm mu times norm v. Norm mu is going to be the square root of 3 squared plus negative 1 squared plus 1 squared. So that's going to be root of 11. And then norm v is going to be root of 2 squared plus 0 squared plus negative 1 squared, which is 5. So this is saying cosine of theta is 5 divided by root 11 times root 5, which is root 55. And so if you want to find the angle theta between those two vectors, this is where on your exam you would pull out your fancy TI-30 X2S calculator that you got from Walmart, and then you would type in arc cosine of 5 divided by 55. Right, so you can ask Google, what is arc cosine of 5 divided by square root 55? And you would want to make sure that you're either looking at degrees or radians, and you want to keep that straight in your head. I want to say that this is probably in radians. Yeah, that's probably it. Let me see if it changes whenever I say in degrees. Yeah, okay. So this is about 48 degrees, or 0.83 radians. And so that's how we answer this type of question about the angle between vectors. But again, you guys already memorized that formula. And so as your answer, you can just write 0.83. Does that make sense?
And it has to be in rating.
Whenever I'm grading your exams, I'll look for either one. So if you had reported this in degrees as your answer, I'll give you full credit. I'll make sure that my answer key has both, so I'll check for both. But either one would be the correct answer. Okay, so new example is find the value of the dot product u dot v if we know that norm u is 5, norm v is 6, and then the angle between these vectors is 30 degrees. So again, we have this little formula memorized that says cosine theta is equal to u dot v over norm u times norm v. So that means cosine of 30 degrees is equal to u dot v over 5 times 6. What is cosine of 30 degrees?
Root 3 over.
Root 3 over 2. Yeah, so you can tell you're going to need to memorize your unit circle, or like, I guess you don't need to because you'll have your calculator, so you could type in your calculator cosine of 30 degrees. Anyways, that's root 3 over 2, and that's equal to u dot v over 30. And our original question was asking, what is u dot v? Well, I just have to multiply both sides by 30, and then u dot v is just 15 times root 3. Does that make sense? So if you had this formula memorized, it should be pretty quick and easy to answer that type of problem. Okay. I've said this in a previous lecture, but we talked about the standard unit vectors I, j, k as being 1, 0, 0, 0, 1, 0, and 0, 0, 1. So notice that I, j, and k are orthogonal to each other. If you were to take the dot product I dot j, or j dot k, or I dot k, all of those dot products would be 0, so that means they are all three orthogonal to each other. Okay, so we're asking what is the angle between this vector v and this vector k. We know cosine of theta is going to be v dot k over norm v times norm k. I shouldn't use a dot because that might be confusing with the dot product. Now notice v dot k is just going to be the third entry in v. Right, because the first two entries are going to be multiplied by zeros in the k vector. So I'll have like 2 times 0 plus negative 3 times 0 plus 4 times 1. And so that's just 4. It's only the third entry in v. And then in the denominator here, what is the norm of k? Yeah, the norm of k would be square root of 0 squared plus 0 squared plus 1 squared. And so that would just be square root of 1, which is just 1. And so in my denominator, I just have to find the norm of v. So it's actually a pretty simple question when you're asked what is the angle between any vector and one of these standard unit vectors, I, j, or k. It's the numerator is always just going to be, either the first or the second or the third entry, and then the denominator is just going to be the norm of your v vector, because the norm of a standard unit vector is always just 1. So these are the same types of questions, but they're just a little bit simpler. The norm of v is going to be square root of 2 squared plus negative 3 squared plus 4 squared. So that would be 4 plus 9 plus 16, which is 29. Yeah, 29, square root of 29. And then to find this angle, you're just going to take your calculator and do arc cosine of 4 over root 29. So arc cosine of 4 over square root 29 is 0.73 radians. So the next question down here at the bottom of my screen says, what is the angle between my vector v and a lot of times in this class, whenever we have a three-dimensional vector, we're going to be able to represent it with an arrow in three-dimensional space where the tail of the arrow is fixed at the origin, and then the tip of the arrow is going to be pointed to some point in three-dimensional space where we say that the entries of my vector correspond to the coordinates x-coordinate, y-coordinate, z-coordinate. So let me draw a little picture. This is my xy plane, and then here's my z-axis, making it three-dimensional. If my vector is 2, -3, 4, that means I go 2 in the x direction, -3 in the y direction, and then 4 in the z direction. 2, -3, 4. Yep. And then I plot a little point, 2, -3. That's in the xy plane, and then I have to go 4 in the z direction. So 1, 2, 3, 4. That's about where my point is in space. So you gotta imagine it's a little bit forward out of the plane towards you. And then we can represent this vector by a little arrow where the tip of the arrow is at that point in space and the tail of the arrow is at the origin. And the question is, what is the angle between this vector and the z-axis, right? So in other words, what's this angle here? But we've already done this problem just prior where we had the k vector 0, 0, 1. We found the angle between this v vector and this k vector. Well, where is the k vector on this coordinate plane? It's this little arrow that points directly along the z-axis, right? This k standard unit vector is just pointing directly along the z-axis. So for the question, what is the angle between my vector v and the z-axis? That's the same thing as asking what is the angle between v and k, and so the answer is once again 0.73. If I ask you what's the angle between a certain vector and the y-axis, that would be the same as the angle between that vector and j. Yeah, because j is my standard unit vector that points exactly along the y-axis. So like this vector would be the j vector, and then I could draw another one. This would be like my I vector. Your I vector would point directly along the x-axis. Does that make sense? Okay. So
we consider the positive like directions,
mhm.
not the negative things.
Yes, that's a good point to clarify, is that whenever we adopt this convention of saying like, you know, if I ask you about the angle between some vector and the x-axis, and I just say, well, just find the angle between that vector and the I vector, what I'm assuming is that I'm taking the angle between the original vector that you're given and the positive x-axis. Yeah, and not the negative x-axis. So that's our convention. Yeah, exactly. And if you wanted to do the negative axis, then you take negative I. Okay. So, more definitions. So you can do more types of problems here. If u and v are two distinct vectors, then we can break up my u vector into two different component vectors. And this is going to be some kind of silly notation, but if you see this, the abbreviation PROJ, that stands for projection. This little subscript V is referring to my vector V, and then this U is saying altogether the projection of U onto my vector V. Okay. Then when you see the letters R, E, J, that abbreviation is short for the word rejection. And the little subscript V, once again, is talking about my vector V. So we're talking about the rejection on V of my vector U. And so this altogether would be the rejection of U from V. And so I know this is a lot to copy down, and this is probably not anything you've ever seen before. But the projection is parallel the rejection is the word we just learned, orthogonal. But regardless of whatever U is, and regardless of whatever V is, we can always write my vector U in two parts. One part that is parallel to V, and another part that is orthogonal to V. So let me draw a little picture to try to illustrate this a little bit. Like, if this is my vector U, and this is my vector V, the projection is going to be if I draw a little line like this, right? So this is the component of U that's parallel to V. And then the rejection is going to be the component of U that's orthogonal to V, like this. And since I drew this in 2 dimensions, orthogonal means kind of the same thing as perpendicular. So I always remember kind of a picture like this. And you can see, like, adding vectors is just whenever you line them up tip to tail like this. So having the projection plus the rejection is just like going along the direction of the purple vector, and then also then after that adding on the green vector, and you end up in the same place that you did if you just followed the U vector. So purple plus green equals U. The projection plus the rejection is the full vector U. Okay. So given the following vectors U and V, and the 2 component vectors U1 and U2, we're going to verify that I'm using purple for projection. That's nice and easy to remember. We want to verify that U1 plus U2 is equal to U, right? We can do that pretty quick. So U1 plus U2 would be the vector 3 over 2 plus negative 1 over 2. So that would be 2 over 2, which is just 1. Then for the second entry, I have 3 over 2 plus 1 over 2. That would be 4 over 2, which is 2. And then for my third entry, I have 0 plus 3, which is 3. And so sure enough, I get my vector U. You can check that one off the list. For my second bullet point right here, I need to verify that U1 is parallel to V. So you might remember this from like Thursday, but if U is parallel to V, or U1, sorry, if U1 is parallel to V, then I should be able to write this. U1 equals K times V, where K is just a scalar. This is what it means to be parallel. Okay, well, U1 is 3 halves, 3 halves, and 0. V is 1, 1, 0. And so what is K? What's my scalar here that makes this equation work? 3 halves. If K is 3 halves, then if I do 3 halves times V, then that gives me my vector U1. Does everybody see that? So that means that these two vectors are parallel to each other, U1 and K. Sorry, K is not a vector. U1 and V are parallel vectors because I can find a scalar K that makes that work. There are situations where you can't find a scalar K. Like what if V was this? Then there's not going to be any K that makes that work, right? And so those would not be parallel. But anyways, that's how we know that those are parallel. So we've verified bullet point number 2 here. Bullet point number 3 that I'm trying to verify is that U2 is orthogonal to V. So I want to check that U2 is orthogonal to V. And how would I know that U2 is orthogonal to V? How do I verify that?
Dot product is 0.
Yeah.
V 0.
If the dot product is 0, then I know that they're orthogonal. So what I want to find is that U2 dot V is equal to 0. This is what it means to be orthogonal. Okay. Now my U2 vector is the vector negative half, positive half, 3. And I'm dotting that with my V vector, which is 1, 1, 0. And so that's going to be 1 times negative half plus 1 times positive half plus 0 times 3, which is equal to 0. So by taking the dot product, U2 dot V, and then we found out that dot product is 0, that's what verifies that those two are orthogonal. Which means I could write this. I can say that U is equal to, the projection of U onto V plus the rejection of U from V, where U1 is going to be the projection of U onto V, and then U2, that is going to be the rejection of U from V. All we did right here is we just verified that U1 is the projection of U onto V, and that U2 is the rejection of U from V. Okay. Now, in that example, we were actually, like I said, given the projection of U onto V and the rejection of U from V, and we were asked to verify that those were true. That's what we did. But if you were not given the projection and you weren't given the rejection, then how would you find them? That's going to be the next thing. This is going to be another formula that you really, really have to memorize. And that is, if you want to find the projection of u onto v, then you're going to take u dot v divided by v dot v. Right? So u and v are vectors, and so u dot v is going to give you a scalar in the numerator. V dot v is going to give you a scalar in the denominator. So you'll have scalar divided by scalar. That will give you a scalar. And so this whole thing right here inside the parentheses is just a scalar. And so a scalar times v, a vector, is going to give you another vector. Of course, we want the projection of v on, the projection of u onto v. We want that to be a vector. And this vector is going to be parallel to v, right? Because it's just a scalar times v. But we do want the projection of u onto v to be parallel to v, so that makes sense. I'm going to skip the proof for right now because we're running out of time. We only have 19 minutes left. If I have time later, I'll come back to these proofs. But essentially, make sure you have this written down in your notes and make a note to yourself that you have to have this sort of memorized. So like make a flashcard or something.
So the dot product is just the magnitude of the projection, right? Of two vectors. It's just the magnitude of the projection vector.
Yeah, you could think of... yeah. Let me think. Like, kind of. This is like another way to write this. It's the same idea. If you took your vector u and you dotted it with the normalized vector v, and then multiplied it times the normalized vector v, that would give you the projection of u onto v. And so this, since that's a dot product, that means everything inside the parentheses computes a scalar, right? And so this is a scalar times a unit vector. In other words, this right here, inside the parentheses, that is the magnitude of the projection of u onto v. And so the dot product of u with the normalized v vector, that's what gives you the magnitude of the projection. Okay, now that we know how to find the projection of u onto v, right? That's what we just said, that's the formula I said, oh, you have to have this memorized, so copy it into your notes. Now that we know how to do that, how would you then go and find the rejection of u from v? What you'd do is you'd go back to this formula. And you'd say, okay, I know my u vector. I just learned a formula for calculating this projection vector, right? We just copied that into our notes. And so now that I know this part of the equation and this part of the equation, all I have to do to find the rejection is take u minus the projection, and that's what's going to give me the rejection. That's how you figure that out if you're ever asked. Okay. Here's an example. We want to find the two components of A that are parallel to and orthogonal to B. So if you're asked for a component that's parallel to another vector B, remember parallel means projection. So I'm looking for the projection of A onto B. And then whenever we're talking about the orthogonal component, that's going to be the rejection of A onto B. So eventually we're going to want to write our A vector as this projection plus the rejection. Sorry, I know I'm changing colors a lot. And that gets in the way.
So we can also say two vectors are parallel if one of them is exactly the projection of itself to the other.
Mm-hmm. That's true. Okay, so we have a formula that we really need to memorize, but we have a formula for the projection of A onto B. Now that formula is A dot B over B dot B times B. Now, A dot B is going to be 4 times 1 plus negative 3 times 0 plus 1 times 1. B dot B is going to be 1 times 1 plus 0 times 0 plus 1 times 1. And then I multiply that scalar times my vector B, which is 1, 0, 1. So this is going to be 5 divided by 2 times my B vector. So this will be 5 halves, 0, 5 halves. Okay, so at this point, I know my A vector. I know the projection of A onto B. So to find the rejection of A from B, this is just going to be my A vector minus my projection vector. So 4 minus 5 halves would be 3 halves. Negative 3 minus 0 is going to be negative 3. And then 1 minus 5 halves is going to be negative 3 halves. Okay. And that's all there is to it. Okay, this is hopefully an interesting example. It says, find the angle between the following two curves at their point of intersection. Okay, but specifically when I say at their point of intersection, let's talk about the point of intersection at x equals positive 1, okay? Because I realize now that there's actually 3 points of intersection between this red and blue curve. And so for us, we're going to focus on this one, and that's going to be our focus of this problem, okay? Now, if I want to find the angle between these two curves, what we mean by angle is this. The angle between curves is equivalent to the angle between their tangent lines. Okay? So what we're going to first do is we're going to find the tangent lines And then second, we're going to find the angle between them, right? That's going to be our little strategy here. But it turns out we don't actually need to know the y-intercept of the tangent lines. We only really need to know their slope, right? Because if I have two lines, and I'm only really concerned about the angle between those two lines, so I'll have like mx plus b, and then y equals, let's call this ax plus c. If I have these two lines, it doesn't really matter what their y-intercepts are, right? They're going to have the same angle of intersection. So I really only care about the slope of the tangent lines, right? What is the slope of a tangent line to a curve?
First derivative.
Yeah, it's just the derivative. So I don't need to find the whole tangent line, I just have to find the derivative. And then finding the angle between lines, well, I can actually just, instead of finding the line, I can just find the angle between vectors, which I know how to do that. So the derivative of x cubed is going to be 3x squared. And then whenever I evaluate this 3x squared at the point x equals 1, that derivative is 3. Then let's think about the derivative of x to the 1/3 power. That would be 1/3 x to the power negative 2/3. If I evaluate that at x equals -1, I have, positive 1. If I evaluate that x equals 1, I would get 1/3. Okay, so now the slope of my first curve is 3, and the slope of my second curve is going to be 1/3. And if I want to write like a tangent vector, the way I would do this is say, let me make my vectors like this. I'll have x coordinate, y coordinate. For this first one, I could write the vector 1, 3, right? And so 1, 3 gives me a vector where the rise is 3, or the change in the y direction is 3, and then the change in the x direction is just 1. And over here, I could write a tangent vector with 1, 1/3. And this is important, but it doesn't really matter what the magnitude of these vectors is, right? And so I could have written 3, 1 if I wanted to. That would be fine. Because whenever we're going to find the angle between two vectors, the angle between the vectors does not care what the length of the vectors are. The angle between two vectors does not care what the length of the vectors are. So what I'm going to do now, call this vector u, call this vector v, and if I want to find the angle theta between u and v, I just have to use this little formula here. So now u dot v is going to be 1 times 3 plus 3 times 1. The norm of u is going to be square root of 10. The norm of v is going to be square root of 10. So this is going to be 10. And so cosine of theta is equal to 3/5. And that means theta is going to be the arc cosine of 3/5. which is 0.93 radians, or like 53 degrees. And again, just to visualize it, that's saying that, oops, not those. These are my curves, x cubed and cube root x. What we're doing whenever I came up with those vectors 1, 3 and 3, 1 is I'm saying, here's a good marker. Here's a vector where I go 1 in the x direction and 3 in the y direction. So there's a vector called u. And then here's another vector where I go 3 in the x direction and 1 in the y direction. So it would be like this. If I want to find the angle between these vectors u and v, I already know how to do that. I already have a formula that we're going to memorize, right, as soon as possible. And so I can find that angle between the vectors, and since I sort of used the slope of the tangent line for these red and blue curves to come up with these vectors, then that's also going to be our definition of what it means to have the angle between the curves. And you can see that this angle theta is also sort of what we would call the angle between the blue curve and the red curve.